Intro chemistry, heat of reaction. The heat change in any process is often denoted by the letter Q. If that's for a chemical reaction, we denote it delta H reaction. And if it's carried out at constant pressure, we call that enthalpy. Many chemical reactions that we do in the lab are done in glassware that's open to the atmosphere, so the pressure would be constant, and those enthalpy changes would be the heat of reaction. We can measure this with the use of a calorimeter. Now, a calorimeter is essentially a thermos. It's a double-walled vessel, in this case insulated by a layer of air. The inner container will have some sort of stirring mechanism and a thermometer so that we can measure temperature changes that occur during the chemical reaction. In this experiment, we are going to measure the heat of reaction for aqueous ammonia reacting with aqueous hydrochloric acid, producing ammonium chloride. To do this, first we have to measure the heat capacity of the calorimeter itself. We'll take 100 mils of warm water. We'll call its temperature TW, W for warm. We'll add that to 100 mils of cold water. We'll call its temperature TC, C for cold. And we'll then measure the final temperature. We'll call that TF, F for final. It's going to look like this. So we'll start with cold water in the calorimeter and measure its temperature over a period of a few minutes. Now, it may rise slightly because the calorimeter is not a perfect insulator, but it shouldn't rise much. At some point here, in this example, about 5 minutes, we added 100 mils of warm water, and the temperature then rose quickly while mixing to a final temperature. Using this information, we can calculate the heat capacity of the calorimeter. So heat is calculated as Q is equal to mCp delta T. M is mass, delta T is the temperature change, and Cp is the specific heat capacity, which is defined as the amount of heat, joules or calories, to raise the mass of 1 gram of water 1 Celsius degree, hence joules per gram per Celsius degree. The heat capacity of water is 4.184 joules per gram per Celsius degree. We'll also need the heat capacity of aluminum, and that's 0.92 joules per gram per Celsius degree. We can say that the heat that's lost by the warm water would be the same as the heat gained by the cold water plus the heat gained by the calorimeter, because both of these are gaining heat. We'll calculate it this way. mCp delta T, that's the heat lost by the warm water. We'll call it negative because it's losing heat. And that'll be equal to the heat gained by the cold water, mCp delta T, plus the heat gained by the calorimeter, C calorimeter delta T. In this equation, the only term we don't have will be C calorimeter, the heat capacity of the calorimeter, and so we can solve for that. Our next step is to mix known quantities of ammonia and hydrochloric acid together in the same calorimeter and monitor the temperature change. So in this part, we're going to combine 100 mils of ammonia, which we'll put in the calorimeter. Now, it'll be at room temperature, so the temperature should not change. After monitoring that for a few minutes, we'll add an equal quantity, 100 mils of ammonia solution, also at the same temperature. So the temperature rise has to be due to the heat of the reaction. We can calculate the heat of reaction in this fashion. We'll say the heat of reaction is equal to the heat gained by the aqueous solution plus the heat gained by the calorimeter. For the solution, we have mCp delta T. In this case, mass will be the sum of the two masses, 100 mils each, or total of 200 grams. The heat capacity of the solution will be a dilute solution of ammonium chloride. Its heat capacity will be essentially no different than that of water, and the temperature change delta T. For the calorimeter, it'll be the temperature change for the calorimeter, which is the same as the water, and the heat capacity of the calorimeter, which we calculated previously. We will take our experimental value for the heat of reaction and adjust it so that it's on a molar basis per 1 mole of ammonium chloride formed. And we'll compare it to the theoretical value, literature value of minus 51 kilojoules per mole. Now, this information in the square box is not something you need to know for the first semester, but you'll cover this in a later course in physical chemistry, so I will explain it briefly here. The theoretical value for the heat of reaction is simply calculated from thermodynamic tables. The heat of reaction is the heat of formation of the products minus the heat of formation for the reactants, and all from their elements. So in this example, the heat of reaction is equal to the sum of the heat of formation of the products, in this case just 1 ammonium chloride, minus the sum of the heat of formation of the reactants, ammonia and HCl. And these again are simply read from tables. The coefficients m and n are simply the number of moles of products or reactants in the balanced equation, and you'll find the value is negative 51 kilojoules per mole. We now have enough information, so let's get started with the experiment. Here's the double-walled aluminum calorimeter. The inner and outer vessel are separated by a rubber gasket and an airspace, much like a thermos. You have an insulating wooden lid and a mixing device. You'll notice the hole in the lid, a place for the thermometer and for adding solutions. We also have a pair of thermometers that are in close agreement. At room temperature, we have 1 molar HCl, 1 molar ammonia, cold water and hot water, and 4 100 ml volumetric flasks. So let's get started with the calorimeter calibration. We'll begin by adding 100 mils of the cold water. I've found these 100 ml volumetric flasks to be very accurate, so I have good confidence that we are in fact getting 100 mils, or pretty much 100 grams of water. So we'll start the stopwatch and begin taking temperature readings every 30 seconds or so until we're confident that we've reached a stable initial cold water temperature. So after mixing for a few minutes, our cold temperature is 11.0 degrees Celsius. It's time to add the hot water. We just leave our stopwatch running. Hot water temperature 47.0 degrees Celsius. We'll mix this for a while, recording temperature and time. Once a stable temperature is reached, we will record that. Final temperature 28.0 degrees Celsius. That's it for the calorimeter calibration. Now we can do the heat of reaction. Start with 100 mils of 1 molar ammonia solution at room temperature. As before, we'll begin taking temperature readings every half minute for a few minutes until it's stable. So our initial temperature here is 22.5 degrees Celsius. Now we'll add 100 mils of the 1 molar HCl solution. We just leave the stopwatch running. And we'll continue taking temperature measurements till we reach a final temperature. Both the solutions are at room temperature, so any increase in temperature must be due to the heat of reaction. So our final temperature is 28 degrees Celsius. That's all we need for the calculations. In the procedure, you will find a table of time and temperature values. Let's take a look at that to see how we perform the calculations with that data. In the lab procedure, in the data and results section, you'll see for determining the heat capacity of the calorimeter, there are several columns of data and results. The leftmost column, which is in white, is a sample. Here is the time and temperature, and using that data, I've summarized it down here in the leftmost column: hot water temperature, cold water temperature, and final temperature. I just took these from the data up here. Here's the hot water temperature, here's the cold water temperature, here's the final temperature. Using that data, I calculated the temperature differences and the heat capacity of the calorimeter. Here's the calculation for it. Recall that the heat lost by the warm water is equal to the heat gained by the cold water plus the heat gained by the calorimeter. So we have mCp delta T for the warm water equals mCp delta T for the cold water plus the heat capacity of the calorimeter times the temperature change for the cold water. So for the warm water, it's 100 grams times the heat capacity of water times the temperature change for the warm water. And then for the cold water, it's 100 grams of water, heat capacity of water times the temperature change for the cold water, plus the heat capacity of the calorimeter, again times the temperature change for the cold water. If you work out those terms and combine them, and then rearrange the equation to isolate heat capacity of the calorimeter, you'll find that 48.7 joules per Celsius degree is the heat capacity of the calorimeter. And that's what I have recorded here. So that's a worked example that you can follow. Now what I want you to do is take the data here in yellow or orange or whatever color this is and work that out for yourself and put the results in these two columns. Take the average heat capacity of the calorimeter here, and you'll use that one singular average value for the next calculation. For the heat of reaction, similarly, the leftmost column is an example set of data that you can look at. I've summarized the results here: initial temperature, final temperature, temperature change, and the heat of reaction. So I've taken that from here: initial temperature 18.1, final temperature 23.0, and the difference is the temperature change. So to calculate the heat of reaction, it's heat gained by the aqueous solution plus the heat gained by the calorimeter. So that'll be mCp delta T for the solution plus heat capacity of the calorimeter times delta T. In this case now we have 200 grams of solution in total times the heat capacity of water times the temperature change for the water plus the heat capacity of the calorimeter, the average value from the previous calculation, times the temperature change for the water. And we work out 4340 joules. We want to convert that to kilojoules, so divide by 1,000. Note that I changed the sign to negative because it is exothermic. Now that's the heat of reaction. For our reaction, we used 0.1 liters of 1 molar ammonia and 0.1 liters of 1 molar HCl, which means we had 0.1 moles of ammonia reacting with 0.1 moles of HCl. From the balanced equation, 0.1 mole of ammonia plus 0.1 mole of HCl produces 0.1 moles of ammonium chloride. So our value is for 0.1 moles of ammonium chloride. We want to know what it is per mole of ammonium chloride. So take our value divided by the number of moles of ammonium chloride formed. In other words, multiply by 10. And so our value, our experimental value, is negative 43.4 kilojoules per mole. From that, you can calculate the percentage error measured minus the true value over the true times 100, negative 15%. Now that's a worked example, and all the results are listed in the white column on the leftmost side. You take the data in these orange-yellow columns, trial 1 and trial 2, and work it out down here. And that concludes our experiment on the heat of reaction.